to the lecture material for systems of measurement for MLT 115. In this unit, we're going to discuss things like common prefixes, measurement systems used in the medical lab field, and how to complete conversions between different units of measurement. There's 2 slides of objectives, this slide and the next slide, and you can pause and read these on your own at this time. This is the second slide of objectives. Again, you can pause this slide and read it on your own. Within the laboratory, we have to work with substances that have different properties. Properties can be either physical properties or chemical properties. Physical properties are properties that can be measured by physical means, such as a thermometer to determine the temperature. And we have some examples here of physical properties such as mass, size, and again temperature, and also freezing point. These are all physical properties of a substance. Next is chemical properties of substances. Chemical properties determine how substances will react with each other in a given physical environment. Chemical properties include things like ionization potential, solubility, and oxidation state. And the reason these properties are important in laboratory setting, in particular medical lab setting, is for us as lab techs to be able to help tell something about the patient or tell about the patient's status to ultimately help diagnose and treat the patient. Okay, let's talk about 2 different ways these different properties can be measured in the lab. And we may have talked about this concept in another course that you're taking, but if we haven't, this will be new information, and if we have, we'll be reviewing this information. But the difference between quantitative and qualitative results. Quantitative is always in relation to a numerical value. Let's say you're running a lab test and you're going to end up with an actual number value. So let's say this sample, you're looking for how much of an analyte is in this sample, and let's say you're going to end up with 8 units is in the sample. So that is quantitative. You're ending up with the exact amount in a numerical value. Qualitative is a non-numerical value. You're either going to get a positive or negative usually. Is it there? Is it not there? Is the substance present or is it not present? And a lot of times in lab this is associated with a color change. Did the substance change from this color to that color? And that color change is indicative of a positive result. If it started out with no color and then it changes to, let's say, blue. Blue is indicative of a positive change. And again, that's just an example. Just that there is just a color change, meaning there is a positive result. Okay, now that we know the difference between quantitative and qualitative, there's something called semi-quantitative. So what does that mean? Semi-quantitative means the results may be measured in a quantitative way, but they're reported out in a qualitative manner. So what exactly does that mean? Well, the measurement or the results are going to be associated with a number in some way, but ultimately the results going to be reported out in a qualitative manner, meaning it's going to be known as either positive or negative, or the substance is there or not in the sample. So let's look at an example. So here is our example. The substance A has to be greater than 5 to be positive. Our result is 6. We're actually going to be reporting out this result as positive because this result was 6, which is greater than 5, which is our criteria. So this is associated with a number, but it's not associated with an exact number of analytes that's present in the substance. So it is semi-quantitative because it's associated with a number, but it's not associated with an exact number. And in order for it to be considered positive, it just has to meet certain criteria of a number. Let's take a look at another example. For substance B, it has to fall between a range of 20 to 30 to be positive. The actual result when the sample was ran came off to be 15. Okay, so does that fall within our criteria of 20 to 30? No, it doesn't. So ultimately, this sample is going to be negative. And again, this is going to be semi-quantitative because you're associating with a range of numbers. You're not getting an exact number, and you report now a positive or negative result. So it's semi-quantitative. For both these examples, for substance A and substance B, I give you an exact numerical result for both in order to be able to see and visualize the answer. But in a real situation, when you're looking at a semi-quantitative value, you're probably not going to get an exact result like we got. For instance, in substance A, I give you the exact numerical value of 6. You probably wouldn't be getting an exact numerical value of 6. You'd just be getting greater than 5. And then you can interpret that as positive, semi-quantitative. And then for substance B, you would just be getting a less than 20 as a result. And then you can interpret it as your negative. In the systems of measurement, the units of measure are defined by numerical descriptions. A unit of measurement defines dimensions or magnitudes of something. There are 7 basic dimensions, and these include the amount or number of units, mass, length, time, temperature, electric current, and luminosity. There are several different systems of units of measurement out there, and basically a system of measure is just a group of units, and the 4 that are the most common is the U.S. customary system, or the USCS, the British imperial system, or the BIS, and the metric system, and then the international system, which is known as the SI. We're mainly concerned with the metric system and the international system and the medical laboratory field. Okay, like I said, we're mainly interested in the metric system and in the international system in the lab. And in the metric system, the primary units are the gram, the meter, and the liter. The basic units of measurement associated with an international system are the kilogram, which is associated with weight, the meter that's associated with distance, the mole that's associated with the amount of a substance, and a lot of times you'll use moles in your chemistry classes, Kelvin that's associated with temperature, second that's associated with time, ampere that's associated with electrical current, and candela that's associated with luminosity. Within our metric system, we have different prefixes that we can use before our base units. But let's first look at our base units. What was our base units for our metric system? Our base units was our gram, meter, and liter that we just went over on the previous slide. And our grams, meter, and liter is going to represent our 1 position or our base position. So if we were to go above or below, we're going to have to add a prefix to or in front of those words. So let's say we're going above 1,000. We're going to have 1,000 grams of something. Okay, so 1 kilo of something is 1,000 grams. Okay, so it's 1 kilogram equals 1,000 grams. Okay, if you're going below, let's say something is 1/10 of a liter. Again, liter is one of our base units. It's going to be deci. 1 deciliter is equal to 1/10 of a liter. Okay, if you have something that is 1/100th of a meter, then you're going to have to add the prefix of centi. So 1 centimeter is equal to 1/100th of a meter. Okay, and finally, if you have 1/1000th of something, and they're giving you grams here, okay, you need to add milli in front. So 1 milligram is equal to 1/1000th grams. This is a continuation of some prefixes for the metric system. If you look down here at the bottom, this starts with our kilo. We already talked about a kilo is 1,000 grams. If we're talking grams, that's our base unit. But any of our base units could use these prefixes. And next up would be meg, giga, and tetra, and then so on. The ones that are in this blue box on this slide are the ones that are going to be more common, but any of these could be used as prefixes. Also, the second column is showing you other symbols that could be used for those prefixes. The third column is showing you the actual numerical value of those prefixes. The fourth column is showing that you could write those values out in exponents, so you could write it out as in the power of 10, so you don't have to write all those zeros out. And also the different names for those prefixes. So kilos associated with 1,000, megs associated with million, gigas associated with billion, tetras associated with trillion, and so on and so on. On the previous slide, we looked at mainly prefixes that fall above our base units, like our meters, liters, and grams. And on this slide, we're looking at mainly prefixes that fall below our base units. If you'll look here on our chart, our highlighted line across the chart represents our base units in our one position. There's only two on here that are above our base units, and that's deca and hecto. When we're working with our metric conversions, we're going to be working with numbers down to about pico. Okay, so know everything from pico up to through your base units to about, let's see, kilo on the previous slide. One last thing I want to mention about the prefixes before we move on is don't get confused between deca and deci. Okay, some students get those confused or get them switched. They're totally different values. Your deca is above your baseline and it has a value of 10. Okay, the deci has a value of 0.1. It's below your base value. Okay, sometimes you'll see this represented as D E K A versus the C. Also recognize that you'll usually have this A with the if it's talking about deca, you'll have a DA, and if they're talking about deci, you'll just have a D. Okay, so make sure that you know the difference between those two, because those can be confusing. Time is another important measurement in the laboratory. We use the SI system's basic unit, which is seconds. We measure things like enzyme activity in seconds, again, which is the international units. We also use time to identify specimens, when things were collected, the time that things were run, when reagents were put into use, when things expire. We also use the Julian calendar. This is when we have a calendar of 365 days and a leap year, and we're going to look at an example of that on the next slide. Okay, these are examples of our Julian day calendar. A regular year has 365 days, okay, in a regular year, but a leap year has 366 days. Okay, so why does it have 366 days? It's because a leap year is where we add an extra day to the end of the shortest month of the year. So our shortest month is February. So on a leap year, we have a February 29th, where on a regular calendar year, we usually don't have a February 29th. February usually ends on the 28th. So we usually have a leap year about every 4th year. And the reason that we have a leap year is to keep our calendar in alignment with the Earth's rotations around the sun. The next unit of measurement we're going to talk about is temperature. And temperature is the tendency of matter to gain or lose thermal energy. And it's measured in degrees. Okay, and there's some different options out there for units with our different systems. In the U.S. customary system, we use the Fahrenheit system for temperature. In the metric system, they use Celsius, and that's usually what's used in the laboratory. And also in the international system, there is kelvins. And we're not going to worry so much about kelvins, but just know that that is a temperature measurement as well. Within the different measurement systems, different temperatures are equivalent to each other. So let's take freezing water, for instance. Okay, let's look at freezing water to start with. Certain temperatures within the different systems are equivalent to each other. So at 0 degrees Celsius, water is going to freeze. Well, that is the same thing as 32 degrees Fahrenheit. Well, that's the same as 273 degrees Kelvins. Again, that's equivalent to each other. At all those same temperatures, depending on which actual measurement system you're using, at each of those temperatures, water's going to freeze. Okay, let's look over here at boiling water. Let's look at the equivalent temperatures. At 100, water's going to boil for Celsius. At 212, water's going to boil for Fahrenheit. For kelvins, water's going to boil at 373 Kelvin. Okay, again, all these are equivalent. And again, you don't have to be so worried about kelvins. Mainly know and memorize the temperatures that water's going to boil for Celsius. And for Fahrenheit, also the freezing point for Celsius and Fahrenheit. All this is the same information that we just went over on the previous slide on the image. This is just written out in bullet point form for you. But again, just know your freezing point and your boiling point for pure water for Celsius and Fahrenheit. Okay, temperature conversions. If you need to convert Celsius to Kelvin, this is how you're going to do it. 0 degrees Celsius equals 273 degrees Kelvin. So to convert Celsius to Kelvin, you would do your Celsius plus 273 in order to get kelvins. If you want to convert kelvins to Celsius, you would take your kelvins and subtract 273 to get Celsius. Now let's convert Celsius to Fahrenheit. So before we get down to the formula, let's look at a couple of things. 1 degree Celsius is equal to 1.8 or 9/5 Fahrenheit, and 0 degrees Celsius is equal to 32 degrees Fahrenheit. So keep that in mind when we're looking at our formula. Our formula is degrees Fahrenheit is equal to 9/5 times the Celsius plus 32. Well, remember what we said up here. 1.8 is the same as 9/5. So we can change this 9/5 to 1.8 when we're actually doing our calculation. So let's look at an example. Our example is going to be, let's convert 45 degrees Celsius to Fahrenheit. Let's write down our formula. F equals And let's use the 1.8 for our 9/5. And then it would be times our 45 degrees Celsius plus 32. Guess just plugging everything into our formula. So F equals, and using our order of operations, 1.8 times 45 is 81. And then plus 32. The rest of our formula. And F equals 113 degrees. So 45 degrees Celsius converted to Fahrenheit is 113. So if we want to convert Fahrenheit to Celsius, we're going to have to change up the formula a little bit. It's going to be Celsius equals 5/9 times Fahrenheit minus 32. So in solving that formula, we're going to want to get rid of the 9 under the 5, and we're going to see how to do that on the next slide. Okay, so like I said before, when we're converting from Fahrenheit to Celsius in the formula, we're wanting to get rid of the 9 under the 5. And a way we can do that is use multiplication. So we're going to multiply this side by 9, and we're also going to multiply this side by 9. So we're going to end up with the 9 on the side of our C, which represents our Celsius. So it can be eliminated on the side with our Fahrenheit by multiplying by itself. This will make the formula much easier to work with. So let's look at an example. Let's convert 74 degrees Fahrenheit to Celsius. So let's plug it in our formula. C equals 5/9 times 74. 74 is going to go in where the F is, minus 32. And then again, we're going to get rid of our 9. So we're going to multiply both sides by 9 to get our 9 with our C. So once you multiply each side by 9, this is how your formula should look. So now you can solve what's in the parentheses. So I'm going to come up here so we'll have a little bit more room. So our 9C equals 5 times 74 minus 32 is 42. So you have 9C equals 210. And then you can divide by 9 to get your C by itself. So C is going to equal 23.3 degrees. So when you convert 74 degrees Fahrenheit to Celsius, you end up with 23.3 degrees Celsius. So here is your answer. This concludes our lecture material for Systems of Measurement for MLT 115. We'll be doing another short lecture on converting metric units using a number line.